All right, thank you. So a bunch of people have already come to me asking me how this is going to work. Is it going to be a talk? Is it going to be a discussion? What is it? Well, discussion isn't a name. So I was asked by Juan to talk a little bit about different kinds of entropy that show up in the black hole context so that we can get them all straight and see how they're related. So I will present a little bit, but you guys should feel free to jump in at any time and make it the launching point for a discussion, okay? So when you aren't talking, I will be saying things. I will even be talking a little bit about my own work, but it's not supposed to be a traditional talk. It's supposed to be you as much as me, okay? Everyone clear on the ground rules? Okay, but you can let me talk for a little while. Okay, so different types of entropy. So one type of entropy that people are discussing a lot, they usually call it entanglement entropy, but it should really be called the von Neumann entropy of a region. So I have some space at one time. If you're a GR person, you call that a Cauchy slice. I divide it into two regions. There's some surface here that's sometimes called the entangling surface. I guess I'll give it a name. I'll call it sigma. And actually, call it gamma. And the entanglement entropy slash von Neumann entropy is just minus trace rho log rho. This big enough for you guys? Okay, so you guys mostly know about that. Then the other thing that shows up is we have, in the context of black holes, Bekenstein and Hawking taught us that we should associate the area, some sort of codimension 2 area of the black hole, with an entropy as well. And that entropy is the area, call this grav. This is the area over 4g h bar. And then if your theory has higher curvature corrections, like you have a Gauss-Bonnet term or something, then there are higher curvature corrections that are always extensive on the boundary. We could talk a little bit about what these are. People used to call it the walled entropy, but that didn't get the extrinsic curvature corrections right. So to the work of like Xidong and other people, we now have a better idea of what these things are. And then there's a third concept that is called the generalized entropy. And for that concept, we just add these two together. So one thing to observe about this first one is the entanglement entropy is UV divergent. But at least the UV divergences are all local. They're extensive with this surface. In the generalized entropy, we add these things together. Okay? And the idea is that the divergences in the von Neumann entropy can be absorbed into redefinitions of the coupling constants of the gravitational entropy. For example, the leading order divergence of the entanglement entropy is just the area, and that would correspond to shifting 1 over g. If there's subleading terms in the entanglement entropy, like there's a log divergence in 4 dimensions, that would correspond to shifting these higher curvature corrections. And people have now worked out enough to know that this seems to be a beautiful, consistent story where it's the same RG flow of the constants you would have had anyway from your one-loop contributions to physics. So the divergences in here are renormalized by here, and at the end of the day, that means this generalized entropy is regulator independent. It's a finite number. And that's why this generalized entropy is a good candidate for the entropy of a black hole. But this still raises two big questions. First of all, yes?
You meant to say that it was a good candidate for the entropy of a combined system containing the black hole?
Yes. So this term would normally include the matter fields outside. So if there's a neutron star orbiting the black hole, its entropy is included. Now, the reason there's divergences is that there's also entropy associated with the quantum fields very close to the horizon, which you might have been tempted to call part of the black hole system. But there's no clear division between. Yeah. That's right. That's right. So one question here is which surface, sigma, is the right surface to use? Because everything I've said depends on picking a surface. It's all very well to say it's, if you have a killing horizon, there's a canonical choice, but it's, yes.
I just want to comment on what Ed said. It's the two of them together, which is the Bekenstein entropy.
I think people usually call this guy the Bekenstein-Hawking entropy.
The area divided by 4 times the renormalized Newton constant is the whole thing, right?
That only makes sense if you renormalize the Newton constant all the way to the IR at infinity. And there's reasons why that's not really a great way to look at it, because there could be that might make a lot of sense if you're renormalizing like the Rindler vacuum state, but if I have an excited state and my black hole is full in like a huge box of gas, it would be a little strange to think of that box of gas as renormalizing Newton's constant.
The near horizon Rindler part of it, I think, it's the Bekenstein entropy, which is the sum of the two of them.
Right, right. Now there's this idea that maybe that was pioneered by you and other people, that maybe if we took our cutoff all the way to the Planck scale, there's some objective UV cutoff, and it's really all entanglement entropy in some sense. That's really a quantum gravity idea. It seems to be equivalent to Sakharov's induced gravity scenario with this RG picture that says there's not really any bare 1 over G term, Einstein-Hilbert term in the action. But that's more speculative than the idea that this works semi-classically. But part of the question is here, what's going on at the fine-grained level? So to start answering that question, one question is which surface should we consider? And another question is there a second law? Normally, if we have an entropy of a thermal system that thermalizes, we expect some sort of second law. Yes? To make it scale independent. Sorry, which of these quantities do you want to be? Oh, scheme independent. Right, so this thing is scheme independent. If you break it up into the specific, depends on what you mean by scheme independent. The certain sorts of divergences depend on your regulator scheme, and certain do not. So one definition of scheme dependence that makes sense just at this level of number 1 is to ask what parts of this are universal. And the answer is power law divergences, including when the power is 0, are not universal, but the coefficient of a log divergence is universal, and the finite piece of the entropy, which is allowed to be non-local, is universal up to a local counterterm. Now, that's a question of can we define something as universal from the perspective of field theory? But if we ask what is universal sort of from the perspective of quantum gravity, this is an actual physical quantity. It's supposed to represent the actual fine-grained entropy of the black hole, the statistical entropy of the black hole somehow. And so the leading order term that goes like 1 over g, that's not universal from the field theory perspective, certainly is a physical number from the quantum gravity perspective. And the reason for that difference of perspective is just that when we're doing quantum gravity, we care about the coefficients in front of the action, of the effective action. We can actually measure Newton's constant. So if something gets absorbed into Newton's constant, we actually see it physically. So it's not necessarily scheme dependent how it splits between these two terms, but the whole thing is a physical quantity. Does that make sense? Okay. So there's several directions one can go here, but let me tell you a little bit about this work that's been done on the second law, because there was actually some controversy over which sort of horizon you should use for defining the entropy of a black hole. And hopefully it'll become clear that this is related to some deep questions about what it means to do coarse graining in quantum gravity. But, so, yes? Everything I said should carry over to the higher curvature case. Now, not every higher curvature action is necessarily UV completable, of course, but at least at the semi-classical level, and ignoring some technical details involving exactly how it works if your matter field includes the graviton, this is pretty well understood now, mostly.
Given that the field theory contains higher curvature counter terms, you always really have to be talking about the higher curvature terms, right?
Yeah, so there's, can you refine your question a little bit? What is it you want to know? Okay. No. So if there's constraints on the higher curvature corrections, it would be something like, for example, in the chems paper, the Gauss-Bonnet term can't be too big. It can't be like classical size. But if we're talking about renormalization, at least if there's order unity fields, we're generating a quantum-sized Gauss-Bonnet, and I don't think there's any known constraints on that. So the semi-classical approach doesn't really know about these constraints, I think. So you could really couple to arbitrary matter fields, and even if it's in the swampland of string theory, I don't think this sort of analysis will tell you it's bad. But you might not be able to probe things that are really nonlinear in these higher curvature terms. There's definitely signs things go bad if you have big higher curvature terms, including with the second law for black holes, so at a more classical level. Like you can violate the second law by merging two black holes if there's a Gauss-Bonnet term. Presumably it's correct if the Gauss-Bonnet term is small enough that it's of stringy or quantum order, then there are presumably corrections to that analysis. Yes? Yeah.
And the difference is, on the one hand, the derivative of the entropy with respect to n. On the other hand, it's the difference between the entropy of a fermion in the hyperbolic plane with boundary condition and the other boundary condition. And it also gives a way to relate the gravitational entropy to field theoretic entropy. We are not subtracting two different hops, but we are subtracting two different boundary conditions.
So, and certainly the n scaling is closely related to the separation between two terms. For example, if I do the holographic entanglement entropy, where I'm relating the entanglement entropy of the boundary theory to the area of an extremal surface in the bulk, then the this thing from the Newton's constant, well, the n dependence really depends on which form of the ADS-CFT duality you're considering. I guess I don't know how it works in, well, I'm not sure whether you can do this in SYK in the same way, but in the classic n equals 4 super Yang-Mills example, this term scales like order n squared. And if you want to know what is the correction at order 1, that comes from quantum fields on this side. So you would add a bulk von Neumann term here. So it's really a generalized entropy in that case. And here we know what the recipe is for sigma. Here the correct recipe is to find the surface that extremizes this thing. In the static case, that's minimizing, but more generally, and we call it Ryutakinagi, but more generally, there's the HRT thing, where if you have a dynamical space-time, you need to find the surface whose first-order variation of the entropy vanishes. And you evaluate the entropy of that surface.
So in this formula, you add two contributions, one from the boundary, the other from the bulk. Is that right?
No, both of these contributions are bulk, and this is equal to the boundary von Neumann entropy. But this one's the bulk one, and this is the area of the surface in the bulk.
Including the first quantum correction, wouldn't it be the same to simply say that A, or gamma rather, is the HRT surface?
Yes, it is. That's what Faulkner, Lukowitz, and Maldacena did. You need to extremize this if you want to go to even higher order in 1 over n. So Netta-Engelhard and I conjectured this formula is valid to every order in 1 over n if you extremize. And this was recently derived by the path integral approach by Aitor and Shi. All right. Yes?
I had a question about the status of this sort of independence of the entropy in effective field theory and how much it's checked. Like if you have Einstein gravity coupled to some heavy scalar, then there's some particular way you divide up the terms, and then if you integrate out the scalar in your effective field theory, or renormalize Newton's constant, but then you don't have a term, and sort of what the status of how explicitly is checked that this is self-consistent in effective field theory.
Let's see. I think some people have begun to do one-loop calculations in some specific cases, but I think it's a tricky thing to calculate entanglement entropy in ADS space-time. So I'm not actually sure how far the explicit checks have gone. It seems more done by conceptual derivations for the most part. But
Do you mean EDS or just the left board?
oh yeah.
In general, EDS.
Because there's a lot more checks of the left board.
Yeah.
Yes.
And I guess it tells you how, because you could just try it for a generic surface, but it may not be self-consistent. It may require a surface to be perfectly.
Okay.
Just one
Yeah.
Yeah, if you have a spherical surface, then you can learn the whole
Yeah, yeah. So,
And compute the vacuum energy from loop correction in a pretty systematic way.
yeah, I mean, there's enough symmetry that I think you can just do it, yeah.
So this scheme independence of the sum, is that supposed to hold for any surface, or does that rely on some special property of it being a black hole horizon?
No, it should hold for any surface with the caveat that it's unclear yet whether what I'm saying is true for the graviton. The graviton's very finicky because, for example, it only makes sense on shell on a solution to the Einstein equations, or the gauge symmetry doesn't make sense. So it's possible that the graviton is finicky enough that some of these things break down. But if we ignore the graviton, then there's no reason we can't define this on arbitrary surfaces. I'd like to think that's true of the graviton too, but I can't promise it to you.
But for your proposal with meta, the quantity in brackets,
Has to be defined off shell.
yeah,
That's right.
so that you're kind of predicting that it should be.
Yeah, yeah, at some level, yes.
There might be a problem with this prediction when you include the graviton.
It's possible. There's, yeah.
But it's not like you have a choice to not include the graviton.
That's right. So this is an important conceptual issue. And if it turns out, that the, I mean, for example, if you actually check what the UV divergences of the entropy are for the graviton, if you do it by the replica trick, then it seems like there's some coefficients you can't work out by that method because it's not an allowed background. But maybe you can just go back to directly thinking of it as the von Neumann entropy, and there's some way, at least dimensional analysis suggests if you think about the von Neumann entropy, the correction should be so one question you could say is, how big are the ambiguities from the fact that we need a covariant definition of where gamma is? And dimensional analysis says that, at least for this term, that should be subleading, so it shouldn't affect the one loop. On the other hand, it might affect this generalized entropy from the area piece, depending on where you take it. So I'd say a lot of this is an open issue. I tried to lay out the open issues with this sort of thing in the appendix to my paper with Raphael Busso and his research group on the quantum focusing condition. I tried to put the state of the art into there, if you're curious. Yes?
About the ambiguity is that it's probably only unambiguous if we pick a particular choice for the definition of the von Neumann entropy, right? For example, the one that comes from Euclidean like if you have a magnetic set, the boundary condition for an abelian gauge field, is that going to be unambiguous?
For a what?
So if you have full magnetic boundary conditions for an abelian gauge field, is it clear that it's going to be unambiguous? The sum of the two terms?
Well, there's no, so I would say boundary, you shouldn't put any boundary condition at all unless you can argue that putting that boundary condition is equivalent to not putting the boundary condition.
But how do you find the entropy if you don't have a factorization of the Hilbert space then?
Right, so it's ideal to be able to factorize the Hilbert space by putting a boundary condition that you've argued is the same as no boundary, but my point of view is that boundary conditions are guilty until proven innocent. You have to prove that it doesn't mess up the physics away from the boundary. I can't just say, oh, I'm going to put Dirichlet-Neumann boundary conditions there and not check, because the actual physics doesn't correspond to a hard wall there. It's a permeable imaginary surface. Yes?
Sorry, so I mean, in the case where you have gravity, then when you compute, say, the Rayleigh entropy mentions, so I think when you say the boundary condition doesn't do anything, I think you have in mind when you compute some nth Rayleigh entropy, and then when you hold the boundary condition in Euclidean entanglement, it doesn't do anything.
Mm-hmm.
And so in the gravity case, because the nth Rayleigh entropy is actually smooth saddle, it's clear that if I have a boundary, if the boundary conditions work in that sense, then they don't affect the answer, and so then you get something that's independent of any choice.
So when you talk about the smooth saddle, you mean like the Luca-Smaldesena method for calculating the entropy, or you?
Yeah,
Calculating for integer n.
that's right. But
Yeah, yeah.
You actually learned that the entropy didn't depend on the choice of good boundary condition. So clearly, if the boundary condition wasn't good in the sense that you just said, you get any answer you want. But even if it is good, then when you combine it with the gravity part, you might believe that it becomes independent of the choice of good boundary condition. But that's, again, only special to the case of extremal surfaces. So how do you know that it will be independent of the boundary condition? Even the field theory part, how do you really know that it will be independent of the choice of boundary?
I don't really know except up to spin 1. And spin 1's not trivial, but I worked it out with Will Donnelly, and we figured out how to make it work. But I think this is an important open issue that should be resolved. So, but one of, but yeah.
One point that Daniel is making is that you can compute, in some cases, in general, you can compute this entropy, entanglement entropy, and both black hole entropy using the Euclidean method. And there we know how to do the calculation.
Right.
So it's only when we try to do it this particular way that we...
Right. So maybe I should say something about why I think it should make sense, apart from just the extremal surface, why this is an important thing to straighten out. So suppose we consider a black hole that forms from collapse. Okay? So we have some matter that falls in. We have a singularity. We have a causal horizon that goes like this. Now, if we're talking about black hole entropy, the simplest possible application of this HRT formula is this part's HRT, is to consider my boundary region to be the entire boundary. Now, if I did that with the thermal field, if I had a thermal field double on the other side I'm not including, we know that there can be an extremal surface that's lodged in the throat, and then we say this represents the fine-grained entropy, the von Neumann entropy of the right-hand CFT. But suppose instead we have a black hole formed from collapse. We now have something like a thermalization procedure. And if we ask, what is the area of the extremal surface on this space-time, the answer is that there's no extremal surface, or to be more precise, the extremal surface is the empty set. So that means that the fine-grained entropy, if we form this black hole from collapse, is 0. Now this makes perfect sense, since most of us believe that the black hole is that the evolution of the CFT is unitary, and therefore, secretly, even though this looks like a thermalization process, it should be the case that the fine-grained entropy, the von Neumann entropy, counting all degrees of freedom, is not increasing. But we do have a black hole, and it does have a horizon, and the area of the black hole is increasing, and at late times, it looks, from external observation, just like a stationary black hole. We want to be able to say that there's a sense in which this black hole does have entropy. And this is a familiar problem. This is the problem that arises in defining the second law with statistical mechanics in general. Once we've got the idea to define the entropy of the universe using the von Neumann entropy, it's really easy to prove the second law from unitarity. It's clear that the entropy at the future time is going to be greater than or equal to the entropy at the past time because it's equal. The von Neumann entropy is preserved by an evolution. But clearly that's not what we mean when we talk about the second law. What we mean when we talk about the second law is that somehow we're allowed to forget about some information because it's been thermalized. So to get a second law, you really need two things. You need unitarity, but the second thing you need, that part's easy, but the part that still makes the philosophers discuss how it works and physicists discuss how this should work in ordinary stat mech with no quantum gravity or black holes is that we need to define a coarse graining scheme. that means that we have some way of saying once the information gets too thermalized, we can replace it with a mixed state that has more entropy. So this holographic entanglement entropy is giving us the fine-grained entropy, and that's associated with a codimension 2 surface. And the fact that it's codimension 2 means it isn't evolving with time. It's just a global in time statement. But we also, if we are going to talk about the second law, we need to talk about coarse-grained entropy, and that means defining what we mean on the boundary side by the entropy on a slice of the horizon or something like that. Yes?
Can I go back to the
Yes.
that I asked earlier? So the definition is entanglement entropy minus Renormalization entropy. So there are theories that you cannot introduce a boundary for preserving all the symmetries.
You think about things with anomalies or?
Say, for example, is this a, you include that in scheme dependence, or is that what you meant in scheme?
Yeah, so there are some things you can do in these theories that still looks like a cutoff on the entanglement entropy, even though you can't introduce a boundary. That's only one way to try to regulate the entropy. So another thing you can do, for example, is you can take the mutual information between the inside and the outside, and you can put a small gap.
And I understand that, but I was just wondering if you think that the ambiguity there is fixed by adding the area term so that the generalized entropy is just clean.
No, I don't think so. I mean, well, I wrote a paper with Nabil Iqbal, and there are some other people who worked on this too, that when you have one of these chiral theories, at least if it's a chiral theory that has a gravitational anomaly, then you don't expect to be able to couple it to gravity. And in such cases, you find that even if you tried to find the theory in flat space-time, that the entanglement entropy is no longer locally boost invariant at the boundary. That depends on the boost angle of the Cauchy slice. Now, you could probably create a theory where the chiral anomalies all cancel, but it's still very hard to write down a boundary condition that's consistent. But
A famous example is the world-shape theory of Aron expression.
yeah. So I don't know whether there's is it proven that there's no boundary condition there, or is it just very hard?
Well, usually in that context, one would like the BRS2 invariant boundary condition. So if you, the accepted answer is that there's none.
Right. And well, I guess the better answer is probably that putting in like a brick wall boundary condition and having it bounce off is a very crude way to regulate the entanglement entropy. And in a theory like that, you should probably be looking for better ways. Oh, people don't usually talk about the entanglement entropy on the string world sheet. Yeah. Was there somebody over there? Okay. All right. So if we do want a second law, we have to start talking about coarse-grained entropies. And there, it's natural to ask what's been shown at the semi-classical level about horizons. But there is now a dispute between sort of two approaches that have been paralleling each other for some time, with even getting a classical second law that says that the area increases. So there's the causal horizon versus approaches related to the apparent horizon. So the causal horizon, a causal horizon is defined as the boundary of the past, of some set of points at future infinity. In the case where we take all of future infinity, this is called the event horizon. So I've drawn here the causal horizon already. The apparent horizon, some people don't like this because it's teleological. It depends on what's going to happen in the future. The apparent horizon is defined in a different way. On a given Cauchy slice, it's defined as the outermost surface whose expansion, which is defined as the rate of change of the area in the null direction per unit area, the expansion has to be 0 at all points along the causal horizon. So given a Cauchy slice, if we pick flat Cauchy slices that are compatible with the spherically symmetric Cauchy slices, the apparent horizon does this. It's not null anymore.
You snuck in spherical symmetry.
I know. So that was just an example. More generally, this is a not very covariant thing to do because we can pick many Cauchy slices. So instead of talking about the apparent horizon, we have to talk about there's many possible apparent horizons. Yes.
You actually drew a one-parameter family.
Yes, so that's another, so this is defined at one moment of time. Then there's a variety of ways to glue them together into one-parameter families to get a codimension 1 surface like the causal horizon. And these go by names like dynamical horizons, trapping horizons.
But is there any definition you could possibly be called covariant? Obviously, if you're going to make choices, you can find all kinds of things.
I don't think there is any definition that's going to be covariant in general. Therefore, if this is the right way to go about it, then I think we need to make a covariant statement. You need to make a statement that's true no matter how you do it. That co-varies with the, with the choice.
In that case, all you should say is that you shouldn't have drawn a one-parameter family. You should have just one, which you said was a marginal trap surface.
You could do that.
That's a meaningful notion, but anything.
Well, I mean, there exist meaningful notions of one-parameter families that satisfy certain constraints. They're foliated by these guys and might satisfy other inequalities, but there's lots of them as well. There's various constructions. So,
But Aron,
yes.
how much covariance should we really be hoping for, given that the entropy is sort of subjective anyway because of your number 2 coarse graining? You know, maybe it does depend on some rather arbitrary choices of how we slice up the bulk, and maybe that's okay.
Maybe it corresponds to the fact that it's sort of arbitrary from the stat mech point of view. I'm inclined to be sympathetic to that. Yeah. But then we could still ask the question, given I've handed you one particular apparent horizon, what's its interpretation as a coarse-grained entropy, for example? Which Netta and I have a recent paper addressing that question. Yes?
If you want to try and define some notion of the horizon of the black hole and make a covariant definition, you should say what you're trying to relate it to. So if you want to describe some kind of coarse-grained entropy in the boundary CFT, you want to say the entropy at what time, and you need to say what Cauchy slice you have.
That's right, that's right.
Once you have a Cauchy slice on the boundary, now you've got lots of options. You can do a maximal volume Cauchy slice, and then you can do a apparent horizon on that.
Right, so one thing you can do, for example, is if I've picked a particular Cauchy slice here, then I can shoot in a null surface. There's going to be a first moment where theta equals a slice of this null surface where theta is 0 everywhere, and now I've just defined an apparent horizon relationally to the boundary here. Yes. That's a construction that we used in the paper I just mentioned. So one question is, which of these two kinds of horizons obey a second law, where in the case of the apparent horizon, we need to stitch it together into codimension 1 horizons to talk about this. So the answer, semi-classically, is that both of them do if you define it right. So I used to think it was only the causal horizon, and you couldn't make it work for the apparent horizon. So if we define what's called the generalized second law for the causal horizon, which I basically proved in my dissertation research, the way you can define that we can define a capital theta as the rate of change per area of this generalized entropy. So it includes the change of the outside matter field. So for example, if Hawking radiation leaves the black hole, we need to account for that, and it's okay for the area of the horizon to shrink. So this thing is greater than or equal to 0 for the causal horizon. I proved this for theories that flow to a free theory in the ultraviolet, but Cassini, Teste, and Torriba have weakened this assumption, so now they can prove it for any interacting, if matter is any interacting CFT in the UV. So this is a general semi-classical result. But you can also make things work for the apparent horizon if you define it properly, because this theta equals 0 thing is very suspicious. It's a classical, it involves the area. Clearly, if we want to consider the quantum version of this, we should, so this apparent horizon, these things satisfy theta is greater than or equal to 0 along the horizon. We should really define what Netta and Raphael call a Q-screen, which is a surface that satisfies big theta equals 0 everywhere. This is in the null direction. And then this implies that along the Q-screen, which is foliated by the big theta equals 0 surfaces, you have theta is greater than or equal to 0 along the Q-screen. Derivative. No, I don't want to write it like that. That makes it look like a contradiction. This is, I'll just write it as derivative of the generalized entropy is greater than or equal to 0, because the whole point is the Q-screen isn't null. So it's 0 if you vary it in the null direction. If you vary it along the screen, it's increasing. Yes? Sure. I mean, I think some of these technical assumptions are in the definitions of these guys. Sorry, is there a specific assumption you have in mind that I should write down? Details. I think these are probably just a defect in their proof and not physically important. Yeah, I mean, I can't really explain. I don't really have time to explain all of that. It looks like both of these kinds of horizons have a second law. And my current viewpoint is, instead of saying who's right about whose definition of horizon is better, well, I don't even want to restrict to horizons. I want to be able to understand, for any surface in space-time, what the quantum gravity stat mech is doing on that surface. So they can both have second laws. That's okay. We just need to explain it both now. Yes?
The second law is supposed to be increase in time, right? But
yes. You have to be okay with the time evolution looking like this.
How do I know it's that way and not the other way?
Well, that's the way it's increasing in area. I mean, it's defined.
But in general, covariantly.
So when this is space-like, it's the outward moving direction. This holographic screen definition allows it to have segments that are time-like. And when you're doing that, they could glue a time-like segment to a space-like segment. That can happen. And then weirdly, in the definition of a future holographic screen, meaning the one that comes when there's a black hole, the entropy is increasing going outwards, and it's also increasing going backwards in time on the time-like zone, which is a little distasteful maybe, but it's not clearly wrong if we don't know how this maps to the boundary side.
I see. I was going to ask about the maps to the boundary. I mean, is there any way I should associate these? To answer your question about the boundary time evolution, is there some way that's been suggested to map?
Yes. So that's what's in my paper. Maybe I'll explain that. So we have a proposal for how to think about the area of the apparent horizon as a coarse-grained entropy. I'm going to start with a bulk statement, and then it will translate into a boundary statement by this trick. Let me say, since I personally aesthetically like the causal horizon better, we tried to make it work first for the causal horizon, and it didn't work. So the thing I'm about to tell you is false for the causal horizon. We proved that. It only works for the apparent horizon. So, yes. The thing I'm about to tell you. So we defined what we call the outer entropy. And it works like this. So here's the black hole. Here's, say, our apparent horizon. So there's a wedge here that consists of all the data space-like outside our apparent horizon. Okay? Now you can ask the following question. You could say, so what we normally do when we have a coarse-grained entropy, one way to find a coarse-grained entropy, the sort of Janesian way, is to say, I specify what's fixed, what I can measure, the sort of macro degrees of freedom, and then I maximize the entropy subject to holding those constraints fixed. I call that my coarse-grained state. So in this case, the analog of the macro degrees of freedom is the stuff that sort of hasn't fallen across the surface, so it's everything in this blue region. That's the outer wedge, which is why we call this the outer entropy. It's the entropy holding the outer wedge fixed. So what we do is we define the outer entropy as the maximizing of the, now this is the one step at this stage where I'm using holography. I'm using that we know it's this HRT extremal surface is the fine-grained entropy on the boundary. If I'm willing to believe that the extremal surface lodged in a black hole throat gives me the entropy, I can do what I'm about to even in asymptotically flat space-time, where we don't understand holography too well. So this is subject to holding the outer wedge fixed. Okay? So this now becomes, at the classical level, it becomes a classical geometry problem to say, how can I so there's the HRT surface is currently the empty set, but I can say, can I replace the geometry back here with some other geometry that makes it not the empty set? It gives there an extremal surface here. So you can do that. We showed you can satisfy the constraint equations with a surface, and only because this has theta equals 0 here, you can satisfy the constraint equations with initial data on which this is a stationary surface. So there's a stationary null surface n, and that if you follow back the stationary null surface long enough, you get an extremal surface that is has the same area as the area of this apparent horizon. Does that make sense? So what that tells me, and we can also prove by contradiction that there's no space-time that has a larger extremal surface than this area of the apparent horizon. So they aren't located in the same place, but they have the same area. That tells me that the maximum entropy I can have on the boundary while holding this geometric data fixed is the area of the extremal surface itself. Now, if you like, you can turn this into a whole thermal field double thing by doing a CPT flip of the data on the other side, and then there'll be another boundary on the other side, and you can think of it as an entanglement entropy. So in that sense, we defined a coarse-grained entropy in the bulk, and it explains the second law for the apparent horizon for the holographic screen, because if I now, at least in the space-like case, because if I have a screen where I move this out space-like, then I'm now doing the same. The coarse-grained entropy here is the same maximization, but subject to fewer constraints. So you maximize something subject to fewer constraints, it always goes up. We've explained the second law at some level. Now, that doesn't relate it to the boundary yet. We had a proposal for that too, but one.
So in the first part of your talk, one of the themes was that the total entropy was the area plus the quantum correction.
Yes.
So here the quantum corrections would be different because there are two different visions. So you imagine in that case that you would look at...
So we'd love to extend this to the quantum corrections and the bulk. We haven't done it yet, and I think it requires some strong assumption, something even stronger than this quantum null energy condition that I think is true for field theory, but it hasn't been proven yet. It's sort of related to the statement that you can always come arbitrarily close to saturating monotonicity of relative entropy. Yes?
I'd like to give an argument for the causal horizon, but I need to go to the blackboard. So,
Come.
can I do it now?
You can do it now.
And I don't think it's an argument against what you said. It's an argument for something else.
Mm-hmm.
Okay, so
I should say, the thing that goes wrong with the causal horizon if you do this is that it's generally not possible to find an extremal surface that has as much area as the causal horizon. In general, the maximum is, yeah. Well, there's other boards.
it's just this one's in the bright light of day, but oh, okay. I can't break my shoulder. Okay. The way I thought about it a long time ago was in very experimental terms. If you were looking at a black hole, like you're looking at the sun, and what do you see coming from the sun? You see radiation, and from the sun's radiation, you can look back at the sun, and you can answer questions about what the temperature is, maybe even what the entropy is, and so forth. So that's the way I was thinking about it. And here is something that is true. I've worked this out in detail for dilaton black holes of various kinds, but I think it's generally true. Here's a picture. Now, I'm not talking about ABS black holes. I'm talking about black holes in empty space, in empty flat space. Here's the causal horizon. Now, I'm going to regulate the causal horizon in a way which we used to call making a stretched horizon. The reason will become clear in a minute. The rule is, and this is for spherically symmetric. I don't quite know how to do it for non-spherically symmetric, but I'm not going to worry about it right now. Just take a point on the actual causal horizon, go outward along a light ray, backward, until the area of the horizon is 1 bit larger than the area of the horizon itself. This is just a trick for making a stretched horizon. So you go back a certain distance, that distance is such as to make the horizon 1 bit larger in entropy, and that defines a surface that looks something like this. By the time you get to this point over here, the actual area of the horizon is shrunk to 0. If you go over to here, you're talking about an area which is just 1 bit, one unit of Hawking Bekenstein entropy. So it's sort of the end of the stretched horizon. The end of the stretched horizon is over here. Just define that, call it the stretched horizon. I think it's pretty clear that if the entropy increases along the mathematical horizon here, if I just go out 1 bit increments, increase. That's not going to change it. It's still going to increase along here, and you can prove that that's true. So it increases along the stretched horizon over here. Now I want to think of an observer who is out at null infinity here, and looking back at the black hole. Here's the black hole. It's looking at it. You will see a Hawking radiation. You won't see any Hawking radiation from down here. The black hole hasn't formed yet. Here is where the horizon forms. Where does the onset of the Hawking radiation happen? Where does, so to speak, the first Hawking particle come out? Now, it turns out in dilaton gravity that happens fairly suddenly enough that you can give a pretty precise location along here. Remember, everything's blown up out here. You can give a pretty precise location where the first photon comes out. And guess what? It comes out from here. In other words, it looks to the observer far away that the temperature, the entropy, whatever it is that's causing the radiation to be emitted, is emitting from this point over here. Namely, where the stretched horizon first started. So I would say that's a kind of observation that the system began to heat up over here. You can go further. You can throw in, well, this might be the picture for a shell being thrown in. You can throw in lots of shells. You throw in lots of shells, and you build exactly the same rule. You take the classical geometry, you go backward one Planck unit, and you develop this sort of stretched horizon, which has many pieces associated with it, and so forth. And sure enough, what you find out is that the Hawking radiation always begins at this point. Then there's a blip on it from this point over here. There's a blip on it from this point over here. All of these points are defined teleologically.
Okay, but I have a counterpoint to this,
Okay.
and related to my previous diagram. And I think we basically have 1 minute left, but I think I want to say this because there was a question about it too. Something about why the apparent horizon here from the perspective of the holographic theory. So in the case where you define this by shooting in this null ray from the boundary, so there's this time t0 here. Netta and I argued that the boundary holographic interpretation, we only can prove that this is true for small perturbations to a killing horizon. But we argued the interpretation of this is that we're maximizing the entropy subject to all feasible experiments that can be done on this boundary only after this moment of time. So a feasible experiment means I can turn on sources, and I can also measure operators. But I can't just run the Hamiltonian back because that's a very non-generic thing. I can't do something incredibly complex. Our restriction is it has to be stuff that propagates locally in the bulk, a lot like Douglas's restriction at the end of his talk. So the thing about you might say, how can you measure behind the apparent horizon? Well, at least perturbatively, the reason you can measure behind the causal horizon is that, which is up to here. I guess I don't want that picture. The causal horizon is here. The reason we can measure behind the causal horizon is the causal horizon and the apparent horizon are separated because matter is falling across the horizon. And I have the freedom to turn on sources, or if you like, turn off sources, to make it so that these horizons coincide. Once I do that, the data that was here, that looked like it was going to hit the singularity, when I can turn on the source that makes it go to the boundary instead, as long as it's outside the apparent horizon. So yes, in your picture, it looks like the Hawking radiation is teleologically coming from the horizon. I agree with that. But if I had turned sources to move the causal horizon back to the apparent horizon, then it would look like Hawking radiation is coming from there, and there's a bunch more things we can measure.
Well, wait a minute now. For any shell that you throw in, I say no matter what you throw in, positive empty shells.
Do you want me to pull your board down, or does it matter? Or do you want this board?
Oh, I don't care. So this is not for ADS. 3ds, I have no idea how to think about this 3ds. But I say no matter what matter distribution you throw in here, you can construct the teleological true mathematical horizon, and then you can stretch it by a process of moving one Planck area backward and construct a definite surface. There'll be kinks in it. Every time you throw something in, there's a little kink, the area grows, and so forth. And what you'll find is that the Hawking radiation comes from here. It continues on as if the black hole had a constant area. Then, when you throw in the next shell, it jumps out a little bit. A little kink in the Hawking radiation there, and they always trace back to the structure of this stretched horizon here. So I don't think this is inconsistent with what you're saying in any way. I think it's just a different definition of which would correspond to looking back and seeing where the Hawking radiation is coming from. You wouldn't see that from here.
No.
Right, so I think it's just a different...
Right. But I'd like to know what's the interpretation of the area of surfaces everywhere. Inside the horizon, near the singularity, way outside. Yeah, that's my goal. Anyway, we're out of time, but there's a big, long discussion later on. So if this raised any questions, you'll be able to thrash it out amongst each other later.